All right. Good afternoon, everyone. How are you doing? Got some fantastic stuff lined up for you this week. Oh, one more in here. Let's get Sophia checked in. There we go. Looks like I'm only missing two of you, Jocelyn and Carlos. Wait, no Jocelyn, no Carlos. Okay, awesome. Yes. So, over the weekend, you will have read about one of those most wonderful of geometric theories, the Pythagorean theorem, right? As well as an introduction to right triangles to go along with that, specifically some special right triangles. And the power of these two ideas, these two theorems combined lets us find all kinds of crazy stuff. So many things in the real world can be turned into or approximated with triangles, and if we do it just right, we can get these special triangles, allow us to solve things very quick, very easy. And we will be practicing some of that today. I'm going to go through a few comments on the problem set and do a couple of examples with you, and then I'll turn you over to the quizzes, and you can show me how much you remember or maybe how well thorough of notes you took with that, and then the rest of the time we'll be starting on this problem set here, which is not due till Friday because we got a short week today. So I've got one slightly larger problem set for you. It's a few more than normal, but there is no problem set 2 to go in this section since you guys work on Friday also. Okay. There's Carlos. Hello. Welcome. Did we get a Jocelyn? No, just the one. All right. Update that. Any questions before we begin? No? All right. Then taking a peek at some of these problems here. The very basic of which is finding the missing length of a right triangle. That is straight up application of Pythagorean theorem. So here's a few practice problems with that. And that serves as a new building block. Now that I can find the missing side of a triangle, I can do things like here in number 4, taking other polygons, drawing extra lines to create right triangles. And now, since I was given these sides, I can find the height of this trapezoid by finding the height of the right triangle, okay? Just a little subtraction to get the base length there. We know the hypotenuse, so we can solve for that third missing side. This allows us to do so much because everything can be turned into triangles. The other thing I want to highlight here is best exemplified with number 7, and that is a throwback to our problem-solving strategies. Okay? Some of these are, I would say, exercises. Number 1, certainly just an exercise. No deep thought required here, just run Pythagorean theorem. But number 7 is a little trickier. Okay? It is not as immediately obvious and straightforward. This says the area of a rectangle is 24 inches squared. Okay, they already give us the area, so already we're thinking we got to work backwards, right? A diagonal of the rectangle measures exactly square root of 73 inches. Okay, odd number to use, but okay. Find the length and width of the rectangle. Now wait a minute, but area uses length and width. That's only, 3 things, and you only gave me one of them. How can I possibly solve for the other 2? Well, we got to make use of this length of the diagonal there. So we're going to walk you through most of this problem and highlight all of these strategies we'll be using. First and foremost, start with a picture. Okay? Draw yourself a rectangle. Note that we know the area. We're looking for length and width. We know the diagonal, so draw that in there as well. We are told it is a rectangle, so we definitely have right angles everywhere here. And now we can see visually that this diagonal creates a right triangle. Oh, this is the section on right triangles. We're probably going to have to make use of either the Pythagorean theorem or the special right triangles somewhere, right? The second strategy we're using here is use a variable. I don't know the length and the width, so let's give them some letters. W and L work just fine. You can call them X and Y if you want. But with that now I can write out an algebraic equation relating those two to the area. That's at least something I know. Okay? When in doubt, start writing down stuff that you do know and see if you can work out something from there. So we're going to write length times width equals 24. There's one equation. Okay. How about this diagonal? Where does that come into play? Well, that's the hypotenuse of my right triangle. So let's write the Pythagorean theorem. Length squared plus w squared, the two legs, equals the hypotenuse squared. So square root of 73 squared is just 73. So we can write that down. Now we've got two equations here, two variables. You know this from Algebra 1. We can now solve this system. It is possible. So it looks like the path forward is just algebra, right? That's at least one way to do it. Although I would look at this thing and notice, hey, wait, these guys are both squared. So even when I substitute here, we can solve for one of them, substitute it into the other, it's still going to be stuff squared, which means this is inevitably a quadratic equation. I don't want to solve a system with a quadratic equation. That sounds messy, okay? Especially with this like 73 here. I have no idea what the factors of 70. I don't think I'm going to factor this easy. So let's implement another strategy. Let's, one, assume that the answers are going to work out nicely. If they don't, then we'll encounter that later. But let's try it. Let's test whether or not we can get integer answers. This isn't going to come out to be like 4.3758, right? Some ridiculous decimal. Let's see if we can find integer values for w and L first. Because looking at this L times w equals 24, there's a specific limited list of possible factors of 24. Right? Find two integers that multiply to 24. 1 times 24, right? 6 times 4 is 24. Just use your multiplication table there. Create a list and then check. Plug those in. See if you get 73 here. I would literally use the guess and test strategy from here on all the factors of 24 and see if one of them gives me 73. Right? If that works, great. I have saved myself a world of trouble with dealing with this, solving a quadratic system. If not, at least I've eliminated some possibilities. Maybe I've narrowed down the range, be like, well, 1 was too small and 2 was too big, so at least I know my range of where they have to be, something like that. Any questions on that concept? I know it's been a while since we've brought forth the explicit problem-solving strategies, so I'll take the time to highlight them again. Remember those tools at the back of your toolbox. No questions? All right, then let's do a couple of examples together, and we'll finish through the whole thing this time. I'm going to leave you with the rest of 7 on your own. Let's do these ones. And these are both fairly similar to a couple of the problems in the problem set. In fact, very similar to. And they highlight both our Pythagorean theorem and our special triangles nicely. So first off, how high can a 12-foot ladder reach if it must make at most a 60-degree angle with the ground for safety? Okay? If any of you have actually climbed a ladder, you should know you do not set your ladder perfectly right up against the building vertical, because as soon as you start climbing up, it's going to tip and fall over on you, right? You're going to pull back, and fall down like that. You don't want that to happen. So you've got to set it at an angle. So I'm going to implement strategy 1, draw a picture. Here's my ground, here's a building, and here is my ladder. Right, we can make it look like a ladder. Okay, make as pretty or as ugly as a picture as you want. And they told us the angle, 60-degree angle with the ground. So that would be down here. Right, let's highlight that in red. Right, this angle here must be greater than or equal to 60 degrees. Now, quick question, does that mean the best possible reach comes from 60, the maximum, or if I make it smaller, will I be able to reach higher. Let's test that. Let's draw an alternate ladder. What if we made a smaller angle down there? Right? This is definitely less than 60. That's allowed. Okay, this would be safe. The ladder isn't going to tip over on us. Although at this point it might just slide down and hit the ground. You never know. But we can see here that this height is definitely smaller than this height. So we don't want that. The maximum possible 60 degrees is what will let us reach the farthest. So we'll stick with that. So we want to know this height here. We already know the ladder itself is 12 feet. So this is forming, okay, 12, solve h. This is 60. This is a right angle because my height is always measured perpendicular up. Even if the building itself is crooked, my height above the ground is always measured perpendicular. So this is a 30, 60, 90 triangle. So I only need 2 angles to confirm that. Let's make it a little bit bigger. So I have some room to draw in there. Right. So that would be 30. And now I just need to find that missing side from my special triangles. If you don't remember this, go back, check your notes until you do. The special shortcut relationships between the sides. Across from the 30-degree angle is the shortest possible side. The shortest side is also always half the hypotenuse. Okay? In a 30, 60, 90 triangle, the shortest side is half the hypotenuse. So that means this is 6 feet. The other side, the one across from the 60 degrees, that's the wonky one. Okay? It's not a simple half. It takes the short side, so in this case 6, and we multiply by square root of 3. That's the relationship. This is root 3 times bigger than the shortest side, which square root of 3 is an infinite decimal somewhere between 1 and 2. So this is my exact answer. 6 root 3 feet is how high I can reach. And if you want to know, okay, what actually does that mean? Give me a decimal approximation. We can just pull out the calculator. 6 times 3 square root is about 10.39. Okay, almost 10.4, a little under 10.5 feet or so, right? That's how high you can reach. Any questions on that problem? Okay. But this is a great example of how these shortcut triangles make solving quick and easy. Okay? All right, problem 2. 2 planes take off at the same time, and I forgot to insert from the same airport. One travels due south at 480 miles per hour. The other travels west at 550 miles per hour. And I did check, these are fairly reasonable speeds for typical 747 passenger jets. 480 might be a little bit slow, but they're within their averages. So, question is, how far apart are the 2 planes after 1 hour has passed? Okay, we've got a couple things going on here. One, we've got 2 things going in different directions. We want to measure the distance between them. The other thing going on here is notice what they actually give us in the problem. 480 miles per hour. They give us speed, or, well, they give us direction and speed. So technically, velocity. They don't actually tell us the distance. So we have currently no distances. So I first want to work out how far does each plane go from the airport. Then I might be able to find a relationship between those 2 distances to find the distance between the planes. So first we need to know a little something about velocity. Velocity is distance over time. Okay? So if we solve that equation for distance, multiply both sides by t, okay, we can find that distance can be found from velocity times time. I'm given the velocity. I'm told the time, right? After 1 hour, so that's my time component. So it's very simple to find the distance. Let's call the first plane distance 1. And that will be its velocity of 480 miles per hour. Actually, you know what? Since I'm going ahead and multiplying the units, let's do this properly. Miles over 1 hour, right? That's what MPH really represents. Okay? A ratio of how many miles in 1 hour. And multiply that by the time, which is also 1 hour. Oh, hey, look at that. Easy peasy. Divide by 1 hour, multiply by 1 hour. Hours reduce, cancel out. And the only unit left there is miles, which is a unit of distance. So you can see how this equation checks out based on the units. And 1 and 1, it's just 480. Yes, I did that on purpose to make it simple for you. So the distance 1, the first plane gets 480 miles, in this case, towards the south in an hour. How about the second plane? Okay. I'll let you guys do that one. What is distance 2? How far does the second plane get in an hour? Follow the same process. Give me an answer there in chat. In fact, I don't even think you need to write out the computation here. You can see what happens. All right, we're going to do the same thing with plane 2. So that 550 miles per hour multiplied by 1 hour. Hours cancel out, and we get our 550 miles. Right? Don't even need to show the work. It's such a trivial computation there. Yeah, this goes, and the second one does the same thing. Right? So now we have our two distances. But how do those distances compare to each other? Because the planes did not go in the same direction, right? Our directions, I've underlined them because they are important. Let's bring in good old problem-solving strategy 1. Draw a picture. One goes from the airport due south. We'll draw it like that. Right, so I'll call this is our distance 1. That's 480 miles. I'm going to say that represents 480 miles. And plane 2, let's see, compass rose, right? So we've got north-south, east-west, never eat shredded wheat. And it goes west, so that would be this way. Let's make our arrow just a little bit longer, because that's 550. Are they exactly to scale? No. But I want the big one to look like it's the bigger one. It's good enough. And that is distance 2. So this is where the planes now are after that hour has passed. They're here and there. I want to find the distance between them. So draw a straight line. Call that D3. West is exactly perpendicular to south. So what I have drawn here now is a right triangle. And the picture now makes it very clear what I must do. I need to find the third side of a right triangle given the two legs. It's time for everyone's favorite Pythagorean theorem. So let's see, D3 is going to be the square root of 550 squared plus 480 squared. Oh gosh, those are big numbers. Can we make this simpler just a little bit? Everybody see that both of these end in a 0. So I'm going to scale this down just to make the numbers a little bit easier to work with. I'm going to divide everything by 10. Okay, you can totally do this. This is very much allowed. Scale it down, divide everything by 10. So long as you divide all three values by 10. So if I get rid of the 0 here and the 0 here, I have to take off a 0 here, which means I need D3 divided by 10 as well. Okay? So if we treat this to be 55 squared plus 48 squared, I don't get d3 squared, I get d3 divided by 10 squared, right? So I've got to multiply that by 10 to get back to the full size, right? I'm finding the full scale version. But we're going to use the smaller scale version just to make the numbers a little bit easier to work with. Okay? So at this point, you could type it into your calculator all at once. I'm going to go step by step. You can follow along with me. So 55 squared is, oops, what happened there? Oh, it kept my last calculation there. Okay. 3,025 plus 48 squared, 2,304. Add them together, we get 5,329. And the square root of that is, are you kidding me? Let's be honest, raise your hand if you thought this was going to turn out to be some ridiculous decimal value, some irrational result. I totally expected that, yeah. No, it's 73. Can you believe that? Square root of 5,329 is 73. That's so funny because we had 73 appeared again in problem 7. Math is so weird that way. So this turns out 55, 48, and 73 is actually a Pythagorean triple. There you go. So our distance, 3, how far apart between the planes? 730 miles. There you go. Any questions on how we solved that problem? No? All right, then please have out your notes. Get ready for a quiz. Go to joinmyquiz.com, enter the game code 785564. 785564. And in fact, I'll go ahead and paste that into Zoom chat. There you go. Got 3 in already. All right, halfway there. Give you another 30 seconds to join. How many questions? 20 questions. Here, 20 questions on Pythagorean theorem and special right triangles. Okay. And as per usual, there'll be fairly short questions, so much more like the earlier exercise practice, not the more in-depth word problems like you'll find through the problem set. Okay, and as always, retakes will be available. Code will be posted at the end of classes today. They're about 2:30-ish. You can retake that all week to your heart's content, but let's see what you can do now. Okay? How much do you remember from the reading? Or if you don't remember, how good are your notes for checking? I'm still waiting on a few people. Should have a lot more of you in. Okay, those of you in, go ahead and get started. Okay, we'll turn off their music. Oh, see, there's Nine. Okay, code is still up there, still live. You can hop in late. That's fine. Remember, only your best score out of all the retakes counts. So don't be shy. Jump in. Get a few practice problems in today. It will not hurt you. Okay. Christian's got us off to a great start already. Look at that, 100%. See? Couldn't ask for better. But we'll just finish that. When you are done with the quizzes, of course, you can get started on the problem set. Ask me any questions that you find.